Okay, so this scale 1, and this scale 1 kind of gave us more confidence about the functional postulation versus anatomical. And then we did further analysis to derive more subdivisions of the subcortical area that recapitulates different functional connective pattern. So this work is published a couple of years ago, and the atlas is freely available to download from GitHub or the NITRC, and also all the analysis MATLAB code are used to derive atlas also available there. And okay, I'm going to move on to my more recent work. Okay, after mapping, as we know, the brain and the body are densely interconnected via different networks or pathways like the circulatory, nervous, and lymphatic networks. So to understand the brain function, and although we know the brain, of course, controls the rest of the body, but the rest of the body also constantly sends signal back to the brain. So the brain and the body function, they can just dynamically influence each other. And I explore this concept from 2 angles in the past 2 years. The first is from aging aspect. As you can see from the neuroscience hypothesis, is that aging is the result of deterioration across multiple organ systems, and that this deterioration is the root cause of age-related diseases. While another aspect is from the mental and the physical comorbidity perspective. As we know, like probably a lot of clinicians, psychiatrists, you see a lot of comorbidity or physical comorbidity like cardiovascular disorders and the diabetes in people with mental illness. While I also know that cardiovascular disease is a strong risk factor for dementia. So I will mainly talk about the 2 work, one from aging, one from the physical mental comorbidity. So I start with aging. So in terms of aging, one concept is that, or the idea behind that, there's a trajectory of biological aging in contrast to the chronological age. As we can see that as people getting older chronologically, aging is inevitable. And some people, in general, healthy people, they might follow some aging trajectory and might reach a point where they have increased risk of reach the threshold of the risk of disorder and develop symptoms at the relatively later stage of their life. While some people might follow this blue curve, so they might slightly deviate from this healthy aging trajectory and might reach the threshold slightly earlier. While there are some other people, they might significantly deviate from this healthy aging trajectory, and their symptom onset will be much earlier than the rest of the healthy population. So the idea is that if you look at the vertical line where for people all aged 60 years old, their risk of developing chronic illness is very different. So this gives rise to the idea of biological age in contrast to the chronological age, which is underlying or hypothetical underlying age of an organism, can be an organ system, the brain, the liver, the heart, or can be the overall body, and defined by measuring some aspect of the organism's biology. So a lot of studies have suggested that the idea of biological age or the index of biological age can differ significantly from the chronological age and maybe actually a better indicator of the illness risk and residual lifespan, mortality risk, etc. So if we look at the literature, the aging field is very rich. In the past few decades, a lot of studies have been investigating the molecular cellular hallmarks of aging, like I show in the picture here, for example, the genomic instability, telomere shortening, epigenetics, and mitochondrial dysfunction, for example. But most of the aging hallmarks, they are investigated within laboratory settings. So at molecular levels, often rely on postmortem samples or animal models. So they are not organ specific. Some of them are difficult to measure in people who are living. And so why not? So here, it's not when it's not organ specific, it might not be informative in some contexts when we know the chronic illness potentially generally only affects specific organ systems. So if only look at the molecular biomarkers, so there might be a lack of immediate translation of those aging markers to the public health and to develop clinical guidelines to facilitate early intervention or disease management. So we wanted to develop some measure of the organ, what called biological age of specific organ systems. So how do we do that? I will briefly show the framework of the brain age using the brain imaging as an example, or what we call the brain age prediction, which can be essentially using the brain imaging to tell us how old the person's brain look like in comparison to their chronological age. So here is the general idea of a brain age prediction, which essentially we use MR scan, we train a machine learning model to predict someone's chronological age. That's in panel A. While we do, of course, there are a lot of validation stuff, validation of the model. Once we are happy about the model performance, we then use the model to predict someone's age based on their brain scan without knowing their chronological age. And then we unlabel them and we unblind them. So we have we look at the difference between predicted and chronological age. So this gives us an age gap or brain age gap. If the gap is larger than 0, this suggests older looking brain, at least based on the brain scan. While if the gap is smaller than 0, it suggests younger looking brain, always in comparison to their chronological age. So this is the whole idea of brain age prediction. And that's been around for a few years. So in a study, we're trying to adopt the brain age prediction framework to not just the brain, but also different organ systems. And we use those phenotypes like commonly used to indicate the function of specific organ, like pulmonary. We use the measures from spirometry test. And for the renal test, we use some blood biomarkers. So here I listed some of the key measures I used in my study, which are available from the UK Biobank. And there are a few others, it's not listed here. So we use data from the UK Biobank, which is a very rich cohort data set, have recruited around 500,000 people at baseline. They have physical assessment, physiological assessment, blood, urine samples, and also multimodal brain imaging. So they have repeated measure for the body and also have repeated measure for the brain. So this will give us some, not just cross-sectional analysis and also longitudinal analysis. So this is the flow chart or the pipeline of our work. So the idea is that we first we only did analysis in a subset of the individuals who had completed measures we want to use, like brain and the physiological assessment. And we based on those medical history, either self-report or from primary care, from the hospital records, we define a group of healthy individuals, train the organ age prediction model. And then once the model and validated, we apply that to the rest of the sample. So this gives us an organ age index per individual and per organ system. Once we have age gap index, as mentioned, if the gap is larger than 0, this suggests older looking organ, while smaller than 0 is suggests younger looking. Once we have age gap index, we can investigate how the organ aging or how the organ aging is manifest in across the range of chronic brain and body disorders. And we can also look at the environmental and lifestyle factors to associate with those organ aging indices. So some environmental factors might be modifiable, so which means they can potentially be used to develop interventions, for example. And we also look at the health outcome, including mortality prediction, which is a quite commonly used health outcome measure. Okay, so this picture again, is just to recapitulate what I mentioned, the brain and body that are densely interconnected. Because of that, one of our hypotheses is to say, okay, so it's possible that an organ's biological age or how an organ's aging can influence the aging of other organ systems, like interconnected organ systems. So to test this hypothesis, we used the idea of structure equation modeling. Although this is not intervention, so we cannot really have the strict causal inference, but it can give us the directional inference of the relationship between two organ age indices. So this picture is a bit, a lot of information here. I only just highlight this one. Here we show that this diagram essentially tells us the cardiovascular aging has a relatively strong influence on brain age, where a 1-year increase in the cardiovascular age can explain about 30 days increase in the brain age at follow-up. So I can see the body were assessed a few years before the brain imaging. So this time sequence of the assessment gave us the possibility to make that directional influence too. We cannot do the opposite direction because the brain was assessed later. Okay, so another way. So the previous one is more based on the cross-sectional data, the body and the brain T0, while the next one is to model whether the baseline one, the organ age or at baseline will lead to faster aging of some other organ systems. So this would not only use the T0 measure, but also T1 measure to give us the rate of change during the interval between baseline and follow-up. So this graph essentially tells us the advanced pulmonary age will lead to faster aging of the cardiovascular system, which would further lead to fast aging of the renal system and metabolic, and go back to the musculoskeletal. If we're thinking about this as a network, in that case, the musculoskeletal system will be what we call in-degree hub, which suggests that it is a common sequela or consequence of age agent. So it can be influenced by the agent across multiple organ systems, which means it's relatively vulnerable. If we look at we can also model this relationship in the subsystem of the brain, because we're from neuroscience background, or we still have the prior interest in brain. So we have the gray matter system, functional network system, and also the white matter system using different imaging modality. So this essentially tells us advanced gray matter age will lead to fast aging of the functional brain networks, but not the other way around. While we say there's a bidirectional positive influence between functional network and the white matter structure. And then, so this is about the interrelationship between different organ systems. We call that multi-organ aging network. And then the next analysis we did is to see how those organ aging appear in people with chronic disorders. So in this study, we included a list of around 16 different chronic brain and body disorders that has quite a severe or a significant burden in their lifetime, like those major chronic disorders, as you can see, I listed here, affecting different organ system. And here I just show a readout. This is a distribution plot of the computed organ age per disorder group and per organ systems. So the first row is the healthy comparison group, while the other row is corresponding to a different disorder group. So this is a very busy plot. I will just highlight some of the key findings. So one obvious finding is that we generally find those organ systems primarily implicated in some chronic illness generally appear the oldest. For example, we say that the pulmonary system most in COPD, the chronic obstructive pulmonary disease, and the renal system aged most in the chronic kidney disease, and the hepatic system aged most in cirrhosis, and the metabolic system aged most in diabetes. So this all makes sense. But the more interesting part is, and also again, the brain aged most in MS, dementia, for example. But the more interesting part is not just the one-to-one matching. We also say that while the brain generally aged most in major brain disorders like MS, dementia, Parkinson's, people with diabetes, chronic kidney disease, and COPD, their brain also appear much older than their healthy comparison group. Similarly, for the body system, like here is overall body, excluding the brain. We say that while the CKD, chronic kidney disease, cirrhosis, COPD, their body appear much older, appear the oldest. But people with schizophrenia, people with bipolar, people with dementia, their body system also appear much older. So this suggests that not only the chronic disease can be characterized by have their unique organ aging pattern, but across the 16, at least across the 16 chronic disorders, we see that advanced biologic aging extend from the organ primary disease pathology to multiple organ systems. So this suggests that the aging effect is much wider rather than limited to certain disorder organ system. Then we look at the relationship between organ age or organ aging and mortality. At the time of our study, we had the mortality data is available for about 8,000 people. So we started with a very simple analysis, just between group comparison, to see how what's the organ age in those group of like already deceased or passed away, and also those surviving. As you can see that across all the body systems, the effect size is sometimes smaller, but the largest effect size if you look at overall body, appear much older in those deceased group comparing to the surviving group. Similarly, we see the same thing in the brain cohort, that we have smaller sample for the brain imaging data, but again, we still see that brain age appear older in those disease group comparing to the surviving group. We further model using the model the hazard ratio, like to model the more quantitatively estimate the increased mortality risk. So here we are using Cox regression. So here we controlled the chronological age, sex, and a lot of existing chronic disorders and major lifestyle factors, the deprivation, smoking, for example. We say that even controlling all the other potential factors associated with mortality risk, we still say that the advanced organ age or body age will increase the risk of mortality. For example, here, the first bar, so here just to say, each one standard deviation increase in the body age will associate with about 12% increased risk of mortality. So this is the key finding. And also this increased mortality risk is also associated with pulmonary, immune, renal, and hepatic age. We also look at the brain. Unfortunately, we didn't find significant association between brain age and mortality risk. This is in contradictory to a previous work where they find brain age predicts mortality. One possible explanation is we have a much lower mortality rate in the UKB sample, like 10 times lower than the study cohort they used in their study, like Lothian birth cohort. But UKB is a continual follow-up study, so hopefully in a few years or in years later, we can have a better understanding of the relationship between brain age and mortality risk. We also further train a machine learning model to see if we can predict someone's mortality, like including survival time and premature death. Indeed, it works pretty well. If we look at model 3, well, even though we say that of course, we have the chronological age, sex, and existing diagnosis can perform relatively good in terms of mortality prediction. If we further incorporating the body age gap indices, the model is further improved. So this suggests that there will be some unique contribution or additional contribution or mortality prediction comparing to the age, sex, and existing diagnosis. Finally, we also look at the environmental and lifestyle factors that might associate different brain and body age. So this can give us some clue of what we can do to slow our aging. Well, although they are all association, correlational, not causal, but still can give us some hint. For example, the smoking, certainly bad things. Everything on the left side, they are bad things. Everything on the right is good things. So if we can change our lifestyle, for example, stop smoking and do more exercise, education, and maternal nutrition, they can be also beneficial in terms of stop or slowing aging. But also there are some factors like as a person probably can't do that would require the national input from government, whatever. We need to reduce the poverty and also reduce the pollution. And of course, if you can live in some area with more green space coverage, that'll be very good. And so this is the paper. And here just some key summary of our finding, where the one key message is we see a multi-system nature of human aging that, and we mapped the contribution to chronic disorders and mortality. Here we provide not just for an individual organ system, but a whole body multi-organ categorization of biological aging. One key finding is that we see that an organ's biological age can selectively and characteristically influence aging of other organ systems. So there will be some putative organ aging pathways there. And And also for chronic disorders, we see that advanced biological agent extends from organs of primary disorder pathology to multiple organ system. And again, we see that advanced biological age predicts mortality. So now I'll move on to the second part of my talk, which is related in terms of brain-body connection, but more related to the physical and mental comorbidities in psychiatry. Here, as you can see, that all the previous literature already highlighted the pressing or the very urgent need to address the physical comorbidity issue in psychiatry. And here, just some fact, which is depressing. So this fact, as we can see, that the mental illness is associated approximately twofold increased risk of chronic physical illness like the heart disease, stroke, diabetes, and people with mental illness, they're associated with reduced life expectancy of 10 to 25 years, while the majority of years of life loss in people with mental illness relates to poor physical health. So again, this highlights the importance of addressing physical comorbidity. However, there's a lot of previous study based on epidemiology, so the more like epidemiological investigation based on medical records. Well, we know that there's increased risk of developing like all the other physical illness, which leads to increased risk of morbidity, disability, mortality, and further worsen the global health and economic burden. However, the biological relationship or biological understanding of the mental physical comorbidity is still not very clear. Another disadvantage of, or not disadvantage, but shortcoming of, if only look at the epidemiological records, those issues with physical health can be potentially underestimated. Why is that? Because we know there is existing disparities in the healthcare system for people with mental illness. They have a lack of access to adequate primary care. There are also that issue, historic issue with diagnostic overshadowing, which essentially concept like, and there, for example, their liver issue, if they go to say primary care physician, and if they have schizophrenia, the primary care physician will say, oh, your liver issue is very likely due to your mental health, so go to see a psychiatrist, while their liver health issue may not be appropriately addressed at primary care. And also there are some difficulties with reporting and acknowledging medical problems for people with mental illness. Again, if we only look at medical records, we might overlook some aspect of people's mental physical issue in people with mental illness. And also, if you look at literature, a lot of epidemiological study primarily focus on cardiometabolic issue in people with severe mental illness like psychosis, while other spectrum of mental health problem is relatively overlooked. So in this study, we try to do a more systematic evaluation. We look at schizophrenia, bipolar disorder, depression, generalized and anxiety disorder, and dementia as a reference because it's kind of mental but also neurodegenerative. We use a large number of samples from both UK Biobank and different imaging consortia across the world, and which we have over 100,000 people, like has a wide age range. So because here are the phenotypes or organ system, like I'm going to investigate more systematically. But a lot of the phenotypes or measures of those either brain or body system, they vary naturally as a function of age and also differ between males and females. So in order to disentangle the age effect or sex effect with to the disease-related effect, we used the idea of normative modeling, which essentially we first established a normative reference range for each phenotype as a function of age and also in terms of their sex. So they all established in healthy individual, like the normative modeling, essentially like people might be familiar with the pediatric growth charts. So essentially a normative range for a certain phenotype in a certain population. So how does this work? So the main idea, if you look at the model normative reference range, so the one in the middle is the median curve, while from the bottom to the top corresponding to the 5 percentile, 5, 25, 75, and 95 percentile show the normative reference range. If here we come, there's a new person coming, we've never seen this person before. We had a brain scan for that person, And that is that person's cortical thickness value. That person is around 30-year-old female. And we look at the value, it matched onto that curve. So, okay, so this is matched to the median of the population norm. So this person will be considered normal. Well, here comes another person, which is 50-year-old woman. And this is her cortical thickness value, which resides at the very bottom curve, the normative reference, the 5 percentile. So this person will have a division score of this minus 1.97, which is corresponding to the Gaussian distribution. And again, we have the third person, which is 80-year-old woman. That person, even though that person has the same cortical thickness value as the person 2, but that person will be considered normal given her age and sex. So this is the whole idea of normative modeling, so it can better distinguish the disease effect from the age and sex effect. So we use this idea we're not just modeling the brain, but also we're modeling other organ systems. As you can see that the normative modeling, the curve as function of age, some are more linear, some more non-linear. There will be some have larger sex differences, some might be not so different. So we did that for a total number of around 200 phenotypes, from imaging, from the blood, from urine, and from physiological markers. Once we have that, because we know if we look at all the individual 200 phenotypes separately, that'll be too much and make it very hard to interpret. So one way to do that is to condense those phenotypes into individual organ systems. So one organ would have one, what we call organ health score, just one value based on the division score of different phenotypes. I'm not going into the detail of how we calculate the organ health score, which is essentially a weighted sum of division score across organ specific phenotype. So we will end it up with organ health score per organ system and per individual. So this is the finding, and here I plotted the mean value of organ health score per disease group, and so each panel is organ system, while the axis in each panel, the axis indicate this dementia group, schizophrenia, bipolar, depression, GAD, and healthy comparison. So this is a very busy diagram, but the main finding is that across all organ systems, we find that the organ health score on average are much, I'll need to mention that the way we compute the organ health score by definition, if this 0 indicates healthy or within the healthy range, but if the more negative they are, the worse the health of that organ system. So they all appear on average much lower than the healthy comparison group. And to facilitate further comparison or visualization, here is just another way to visualize this data. Here I stratified by disorder group, but each axis in the spider plot is an organ system label. So one surprising finding to us is that what we know, they all consider brain disorder in good way or not, and with certain neural origin. But if we look at the organ health score, it is the body system that seems to appear much worse than their brain health. This is especially the case for bipolar, depression, and GAD. While if you look at dementia, the gray matter also doesn't look very good. But for other disorder group, the brain seems ranked much lower. And so one consistent finding is across the 5 disorder group, the poor organ health is most evident for metabolic, hepatic, immune, renal system, and the poor body health appear to be a more pronounced illness manifestation in psychiatric disorders, not the brain. And finally, we try to see if we can use those division score and to do diagnostic and transdiagnostic classification of those disorder groups. And what we can see, which is also surprising in a way, because while at dementia group, we say that it is the brain phenotypes that provide the most accurate diagnostic classification. If you look at other disorder group, the body system perform not bad, And even for schizophrenia, it's even outperformed the brain. While if for others, it's not great if you look at absolute value of AUC, which is actually the prediction accuracy, but still better than the brain. However, if you look at the transdiagnostic classification, indeed, it is the brain that provides most accurate transdiagnostic classification between pairs of distinct psychiatric disorders, especially for dementia, is most accurate. And for schizophrenia, reasonably accurate. However, it's not that good for other three, but even that's better than the body. So here is just to showcase some of the transdiagnostic brain features of the most performing because here we see the most accurate one is for dementia. So I just think maybe now just show some brain rendering in case people are interested in dementia. So what we see that the strongest features that distinguish dementia from bipolar, depression, and GAD is the hippocampus, the hippocampal volume. While hippocampal doesn't contribute too much for the dementia schizophrenia classification, maybe because we know the schizophrenia has very their hippocampus also heavily affected, so which might be the reason. Again, so panel B is the white matter, and similarly, the differential the feature pattern for dementia versus bipolar, depression, GAD really distinct, while there's some difference for dementia versus schizophrenia, mainly the phonics is the top one. And okay, so here's the paper published just a month ago, and the key point of our work is that we show that different psychiatric disorders that do have quite relatively different body and physical health profile, while individuals, and more importantly, we say that individuals diagnosed with the psychiatric disorders, at least the 5 groups we studied, not only categorized by deviation from normative reference range for brain phenotypes, at least the imaging-based brain phenotypes, but also present considerably poor physical health scores across multiple body systems. And that this is more surprising, or another important finding is that we find that poor physical health was a more pronounced illness manifestation of neuropsychiatric illness than brain health. Well, it's a comforting or things for our doing neuroimaging research. We say that the brain actually can distinguish different pairs of psychiatric disorders, but which means there do some like brain or neural origin differences like drive different symptom spectrum. Again, I think here are another 3 main messages, like not just for academia, but also for the public and the clinicians. So it seems like there's general manifestation of physical health issues across different psychiatric groups. And we want to tell the message that the management of psychiatric disorders should not just focus on the brain or the psychiatric symptoms, but should also acknowledge the importance of poor physical health. So there are some discussing about that point, but here we provide more biological evidence to further support that notion. And hopefully that will be adopted in clinical practice somehow. And also we want to suggest that the routinely monitoring body health and integrated and holistic approach of managing mental and physical health is important and can potentially save the government a lot of money, be cost effective because they might be beneficial and also address adverse impact of physical comorbidity in people with mental illness. And that's it. I would like to thank all my collaborators in Melbourne and also in other cities, and thanks all the participants and the fellowship, and thanks Barbara for organizing this, and thanks everyone for your attention.
Okay. Thank you, Ye, for such a fascinating talk.